An angry bird sits on a hanger that hangs by a pair of strings from the ceiling. If the mass of the hanger and bird combined is 154 grams, what is the tension force in the strings? So we got a nice picture there. So I think I can jump straight maybe into the FBD since I've already got such a nice picture of the situation. I don't need to make another one, I think. So the system we're looking at here is the bird and its hanger. And I think it's fair to say that there's going to be a total weight for that, right? So that's going to be represented by this gravitational force and corresponds to mass times g for the mass that's given, but we're not necessarily being asked to find that right now, so we won't worry about that for right now. But we also have those two strings that are kind of symmetrically holding all of this up. And so the rule says the tension force should point along those strings and generally away from the system. So since this is our system here, the direction of these two forces should point, again, along the direction of those strings, which is kind of, it looks like at 45 degrees, and away from it. So that gives me two forces here like this. And maybe, I don't know, if you ask, like, what name should I give these two forces? They're both tension forces, so I could maybe say, hey, there's Ft, and if I wanted to, I could say maybe Ft sub 1, and then call this other one Ft sub 2. But I don't know if I have to, because there's symmetry here, and I actually think both of these, because of the symmetry, are going to be equal to each other. So technically they're different force vectors because they point in different directions, and maybe at some point in my analysis I'll want to say something about that. But since they're both definitely have the same magnitude, and I'm just going to label them with their magnitudes here, I'm just going to call that F sub t without a subscript. Now, since the bird is at rest, I think this is kind of a Newton's first law situation that I feel like corresponds to that the sum of the external forces is equal to 0, which is really the same. I think at other times I've kind of said, well, that's meaning that the net force is equal to 0, which means that the sum of the two tension forces. So in this equation, I am going to go ahead and use a 1 and a 2 to kind of distinguish the two tension forces, and maybe 1 is this one and 2 is this one, and hopefully we can just remember that. If we switch it up, it probably won't matter, I think, because of the symmetry here. And then there's gravity is equal to 0. And this equation, like usually when I see three forces is equal to 0, and especially if I know there might be a right angle somewhere in there, most of the time I'm inclined to do a geometric analysis rather than try to like work out components and do something more analytical, which is a lot more work, if you might recall from the last chapter. So again, I'm not going to do that here because I think we do have a right angle between two of the forces. But if I kind of look at, like, let's say I start out there with tension force number 1, that's the one I think it was, and then I add to that in a vector sense tension force number 2. So tension force number 2 is at this other angle there. There it is. And then I have to add that to gravity, and to reflecting the fact that the net force is equal to 0, that should return me back to where I was. And if it didn't, it means I might need to adjust my picture to make that make sense. So now I've got the, I'm going to label this with magnitudes and therefore drop the 1s and the 2s in this picture because I know that they are equal magnitude, but there is the force of gravity. And okay, so how can we interpret this? Well, this is a triangle, right? And we can calculate the force of gravity, right? Because force of gravity is equal to the weight, which is equal to mg, which is equal to 0.154. I'm going to convert that 154 grams into kilograms multiplied by 9.81. I had to move something there. I'm getting to the edge of my region I can write easily. Meters per second squared. And that is something I could definitely calculate if I wanted to. Let me go ahead and do that real quick. I haven't done that yet. So that gives me like a value of like 1.51. I'm going to go ahead and write the whole thing because it's not too long. And that should be in newtons. I don't want to round off yet because that's not the final answer. This, however, I think there's a right angle here, and that makes this an isosceles right triangle, which guarantees that these two angles here have to be 45 degrees. I think that kind of made sense given the two 45 degrees I was given right here. But keep in mind, these angles are physical angles between the strings and like a ceiling here. And the 45 degrees I'm talking about here are angles between forces. So sometimes be careful if you make that leap. But in this case, I think given the fact that this right angle is definitely there. And how does that make sense? Well, see that there's definitely a right angle between these two strings here, and that means there has to be a right angle between the tension forces in this original picture, which kind of, it's from that I'm concluding this must be a right angle, and that pretty much again makes this an isosceles right triangle. And if you remember the way that works, well, okay, well, there's maybe a couple ways looking at this. Is definitely, I could say that means there's a 45 degrees here. And if I want to figure out what one of those tension forces is, if I look at that triangle there, I think I could do either sine or cosine on this, right? Like I could say, okay, that if I take FG, which I've already calculated, but for brevity I'm just going to call it FG, and if I wanted to, I could multiply that by the sine of 45 degrees or the cosine of 45 degrees, because there's kind of two of those here, and there's also two tension forces, so whether it's opposite or adjacent, I don't know. But that gives me something straightforward to do. You might also recall that this is the same as square root of 2 over 2, sine of 45 degrees. So really, if I just take this number in my calculator, this 1.51074 newtons, and then multiply. You can either multiply it by root 2 over 2, or it turns out that's equivalent to just dividing by the square root of 2, which may be easier to enter into your calculator. And when you do that, you get a number of like 1.06825, etc. And maybe in this case, that'd be okay to round off to 1.07 newtons, giving me a solution that I can now go ahead and check. And with that amount of round off, it is correct.